This is lesson 4.3, and we're going to be modeling quadratic functions. We have some real-world problems to do today and just some different types of problems involving quadratics. So it's, again, kind of an extension of the base knowledge of quadratics, and that's why I like this chapter. All right, so problem 1 says, a parabola contains the points 0, 0, -1, -2, and 1, 6. What is the equation of this parabola? So it's kind of crazy, right? If I gave you 3 points, or even like of a parabola, or even gave you like these 3 points of a parabola, we can figure out the equation of the parabola just given 3 points. And the reason we can do that is because we know that the standard form of an equation looks like this. And as long as I have 3 points, I can put those points in for x, the xy of each of these equations 3 times, and I can find out what A, B, and C are. There's a little bit of algebra here, and I kind of wish that there was more room for this problem, so write small when you do this. All right, so the first point is point 0, 0, and I'm going to put, this is like x, and this is y. So this is going to be 0 equals A, I don't know, and I'm going to put, this is 0 squared, but that's going to be 0 plus B times 0 plus 0. Or plus, excuse me, plus C. I was totally confused there. I replaced 0 with my x's and my y's. And so, interestingly, when you just simplify this a little bit, this is 0 equals 0 times anything is 0. So that's 0, and all I have is C equals 0. So I know C equals 0. So that's this one right here. Now I'm going to pretend like I don't know that for a moment, and we're going to go ahead and do the other one. So now I'm going to use, this is my x and this is my y. So -2 equals A times -1 squared plus B times -1 plus C. And when I do this one, this is -2 equals, here I have -1 squared, which is 1. 1 times A is just A. And then minus 1b, so I'll say minus b, and then we could say plus 0 here, right, or not say anything at all. But basically, if I want to write this in standard form, so it's like standard form of a linear is like a plus b equals some sort of c thing like that, or when you have like equations, you think of these kind of when we did systems of equations, you have like equations like this, and then you would multiply one of them by something. That's kind of what we're doing here. It's just our variables are A and B, not X and Y. So I'm going to say, I'll just say A minus B equals -2. I basically just swapped the left side for the right side. So I have that equation like that. I have a third point, and I'm going to do something with that. So that is this point, 1, 6. So y, I'm going to using this equation here, 6 equals A, and then 1 squared plus B times 1 plus C, which I know is 0. 6 equals 1 squared is 1, so that's A plus B, then plus 0. So if I write this one in standard form, A plus B equals 6. So I have that one, and I have this equation, A minus B equals -2, and I can use elimination here. I have 2 equations, 2 unknowns. My unknowns are A and B, and I can easily add these together, and it works out pretty nice. This becomes 2A equals 4. The B's drop out, so A equals 2. And then I can use either this equation here or this one here, it doesn't matter, to find B, and B must be equal to 4. So my A, B, and C are, I'll just write C here, 0. So it wanted us to, what is the equation in standard form? So standard form, again, is this equation right here. So my equation is y equals, A is 2, x squared plus b is 4, 4x plus 0. You don't really have to write the 0 for c, but I did there anyway. All right, problem number 2. Campers at an aerospace camp launch rockets on the last day of camp, and the path of the rocket 1 is modeled by this equation, where t is time in seconds and h is the distance from the ground, which is in feet I see here from this graph. The path of the rocket 2 is modeled by the graph. So this is rocket 2, and this is, that equation is rocket 1. Which rocket flew higher? All right, well, this rocket, let's go to rocket 2 first, because that's just kind of a little easier. It looks like it was up in the air for about 12 seconds, and it reached its max height at 6, which it kind of does. It reaches its max height halfway along. Looks like it's just shy of 600, there. Maybe it's at, I don't know, 560, question mark, something like that. Rocket 1, I can find, with this equation, I can find the vertex by doing h equals negative b over 2a. So negative 150 over 2 times negative 16. Again, be careful when you divide that. That's like 150 divided by negative 32. So make sure you do things in the right order. I can't tell you how many times kids get that wrong. And then the whole rest of the problem is just wrong. Also, time should make sense. Like rockets in the air, things don't stay in the air that long, right? I mean, even your best rocket that you made at aerospace camp is not going to stay in the air that long. These are not like, propelled rockets that are going to go from one country to the other and bomb them. These are just like little kids' rockets. There's no propulsion other than right at the beginning when it got lifted into the air. So this one looks like it's been in the air. It'll be at its max height here. This guy is at 4.6875 seconds, right? And then what is it going to be? Its height. Well, that's k. So k equals negative 16. I'm going to plug in my h value into this equation. 150 times 4.6875 plus 1. And when I do that, and again, you should make sure you can type this in your calculator. For time's sake, I'm not going through that. K equals, this is disappointing, 352. My dog's going crazy. There's just some loud trucks going by. 352 point, I believe my handwriting says 563. So it only goes up to like 350. That's like right about here at like about 4. So this rocket kind of did this, That was rocket 1. Rocket 2, way better. So which rocket flew higher? Rocket number 2. Hopefully that was your rocket and not rocket number 1. I remember, and then my kids always talked about it at Central. They would always do that. Maybe they did it at Sunrise too, where they let their rockets go. Okay. This problem here is using quadratic regression. Now, I think this problem is very interesting, is why I kept it, because last year in Algebra 2, we did linear regression, and that was kind of interesting because we basically were given tables of things like this, and we basically said to our calculator, hey, use all the points and give us an equation of a line. Well, now we're going to do quadratic regression, which is basically the same, except is we're going to look at these points that it gives us. And, maybe these points are kind of, like this or something. And we're going to say, hey, take these points and tell us what the best parabola would be that fits that data. Okay. And so regression is something that computers do all the time to help predict things. Like if you think of all the COVID stuff and all their predictors, and they have obviously some very complicated models, but they're looking at data and they're trying to figure out what that trend is so they can project into the future what things might be like. And they don't just do it for COVID, they do it for all sorts of things in science. So that being said, let's go to our calculator, and we are going to go to Stat, and then to edit. And if you have anything in your list, you need to get rid of it. And I will show you how in a moment. Also, you need to have list 1 and list 2 there in order for this to work. So if you don't have list 1 and list 2 at the top, you need to add them back in. You can reset your calculator. You can just Google how do I get list 1 and list 2 back in, or you could ask me in class. So how you get rid of the list, what you don't want to do is go up here to the top and hit delete. If you hit delete, that's actually what deletes the entire column, and you don't want that. You just want to clear the data. So you hit clear and then down arrow, and it will just clear the data there, but it doesn't actually blow away the entire column. Clear, down arrow. All right, so there we have that. Now what I'm going to do is in list 1, I'm going to put all these times in. 8, 10, 12, 2, 4, 6. And then always check your data, make sure you didn't do a little thing. Oh, we're going to have to do something here. Let's think about that time. I don't think the time's going to work very well if we use our standard time. So let's think about that. If you're in the military or even the medical field, they don't use like 4 o'clock to, when they talk about the PMs, they just keep going. So let's go back here. If you do this, this would be all messed up if we don't change this. 2 o'clock would be like hour 14. Just add 12 to it. And 4 o'clock would be hour 16. And 6 o'clock would be hour 18. There's 24 hours in a day. So that's going to be better. If you don't do that, it would be kind of messed up. Now I'm going to do what I'm going to do, and this is what we did with linear regression last year, is we can hit zoom stat, and these directions, by the way, are there on your on the side of your notes. I can hit number 9. This will size the data. Now you're like, I just hit that, and my parabola that I did earlier is there, and that's not right. And this is what you need to do. You need to, if you're doing the stat stuff, which is what we're doing, right? You need to turn your stat plot on. Your stat plot is not this y equals thing. It's second stat plot. The stat plot's right up there, and we need to turn a stat plot on. So I hit enter, and then I hit enter again. And now I have a stat plot, and it's going to be using the list 1 and list 2. And this is why if you blew away those lists, you should really get them back. Otherwise, there's some troubles. Now if I go to zoom, and number 9 is zoom stat, my calculator will size the window for the data that I was given. And I can see this kind of looks like a parabola. And I might, as a scientist, go, yeah, I think I want to see what my calculator says that equation is that best fits that parabola. So what I'm going to do is go to stat and over to calc. And if you remember last year, we always did number 4, linear regression, but we are now doing quadratic regression, which is number 5. And we kind of go down to here. And we say, hey, calculator, tell me what the quadratic equation is. And it does. It's y equals, and let's just decide we're going to use 3 decimal places or something like that. All right, so y equals, y equals, oh, no. My stylus was doing so well there, but sometimes when I go back and forth between my calculator, it just dies, and then I have to use this other stylus. All right, so y equals negative 0.469 x squared, because I rounded there, plus 14.716, I believe. X, and then minus 36.121. All right, so that is what we have. That is an equation that would model things. And then that is the answer. If it were to ask for the vertex would be, you could go I see here my notes have a use your model to predict the high temperature for the day and when does that occur. So what you could do now, you have this equation. I know this maybe is not in your notes, but you have this. What's the high temperature of the day? Well, that is going to be the vertex. There's two things you could do. You could type this equation into your y equals and ask your calculator to find the vertex. Or you could do your h equals negative b over 2a, and you could find it that way. Let's just do it with our calculator here quick. So if I type this equation in, y equals negative 0.469x squared plus 14.716x minus 36.121. Make sure that looks all okay. Now I'm going to, let me just graph this to make sure this looks, and it should go through. You can see it doesn't go exactly through all the points because it had to kind of pick and choose a kind of a route that best fit it. But now if I go to stat, we did this in the lesson notes previously to today, 4.2 notes. So I go over to calc and I say, oops, that's not what I wanted to do. My bad. I'm going to graph that, right? I am going, if I want to know what the vertex is, I go second calc here, this calc, not the stat calc. And I say, in this case, a maximum, number 4. And then I can just kind of use my left and right arrows. A maximum is asking for a left bound, so something to the left of it. Right bound, just make sure you're past the high point. So probably this should be good. Do you want to guess? Sure, you can go back and try to get about right where it is or not. It doesn't really matter. And it's telling us the maximum is 15.689. 15.689. And the y value, which is, I think, really what we want, 79.32, let's say. 79.32. So the question was, use your model to predict the high temperature of the day and when will it occur? Well, it'll be 79.3 degrees, not percent, degrees, and that would happen at 1500 hours, which is 1500 hours after 12 o'clock. If you're going to add to that, that is going to be about 3:30. And you can actually convert it and get it really exact by taking this and multiplying this by 60 minutes, and you can find out it's really 3 o'clock, and the minutes is 42 minutes. So that's getting pretty exact. The high temperature is going to be 79 degrees at 3 o'clock, 3:42 p.m. So that's that lesson.